This lecture is about predicative polymorphic lambda calculus. Predicative polymorphic lambda calculus. So before we start talking about predicative polymorphic lambda calculus, let's review system F again. So in the spectrum of programming languages with the polymorphism, system F lies at one extreme end. So if we recall the syntax for system F, we have just a single syntactic category for types. So types, it has function type and type variable and polymorphic type. And in expressions, among others, we have this type application. The system F is a very powerful language in terms of polymorphism, but it has one big downside, which is the type reconstruction is undecidable. So that is, we start with an expression in untitled lambda calculus. And first, we'd like to check if this is convertible to a corresponding expression E prime in system F. Of course, there's an expression that cannot be converted. For instance, omega. Omega cannot be converted to a corresponding expression in system F. So first, we should be able to decide if the given expression E can be converted to an expression in system F. Unfortunately, this problem is undecidable. There is no algorithm that can decide the convertibility of a given expression in system F. And if we think about the source of this undecidability, that is, if we ask the question, why is it that this system F has this undecidability property? It turns out that the source of this undecidability can be traced back to this self-referential nature of system F. Self-referential nature in type application. So what I'm talking about is this one. So this is type application. So presumably this expression E has some polymorphic type, something like for alpha A. Now we are going to instantiate this type variable alpha to type A, and this type A can be any type. And why is this called a self-referential phenomenon? So we can imagine that in the development of system F, we start with types consisting of function types. So this is a set of types, and perhaps we have something like A arrow A. So we start with this function type. Now we'd like to introduce polymorphic types. So we introduce this polymorphic type for alpha.A. And this type variable alpha is literally variable over types. So alpha is type variable, so it's a variable over types. And according to the syntax for system F, this type variable alpha can range over not just these existing function types, but also these polymorphic types themselves. Because there's no restriction on the way that this type A is used in this type application. In other words, there is no restriction on type A here. Any type can be used in type application. So now we start to see this self-referential phenomenon in the definition of system F. So let me summarize the story again. In the beginning, we start with this set of function types, and there's no polymorphic types. And we'd like to introduce polymorphic types. So we extended this set of types. So we start with this inner circle consisting of function types, for example. And then we augmented the set of types with these polymorphic types. So we introduced this one. And along the way, we introduced this type quantifier or type variable. But this type variable can range over not only over this existing set of types, but also the new set of types, which include the polymorphic types themselves. So in some sense, this type variable A is ranging over these polymorphic types themselves. This polymorphic type is ranging over itself, something like that. So it turns out that this is the self-referential nature in the type system of system F, and this is the source of undecidability. So perhaps we can recover this undecidability of a system F type reconstruction by placing some restriction on the way that this type is used in type application. So at the other end, at the other extreme, we have this predicative polymorphic lambda calculus. So it is decidable. So we will see how we restrict the use of types here in type application. And in the definition of a predicative polymorphic lambda calculus, we will not see something like a self-referential phenomenon. So let's start to develop predicative polymorphic lambda calculus. So as we have seen in this example, the problem with the system F is in the definition of this type application, this type A can be any type. But perhaps we could restrict the range of this type variable to the set of existing types of function types. So in other words, in the case of system F, this type variable alpha can range over this function type and also polymorphic types themselves. And why don't we limit the application only to these function types? That is, we disallow this one. We only allow this one. Then perhaps we can get rid of this self-referential stuff and then recover this decidability. So that's the plan for developing this predicative polymorphic lambda calculus. Right, so that's the idea. So let's start to develop predicative polymorphic lambda calculus. So in the case of predicative polymorphic lambda calculus, we'd like it to distinguish between this set consisting of function types and the outer circle consisting of polymorphic types. So in the case of system F, there's no distinction between this inner circle and outer circle, as indicated by this single syntactic category covering all types. So we have only single syntactic category for types. So there's no distinction between this inner circle and this outer circle. There's no distinction in system F. But now we'd like to make a strict distinction between this inner circle and the outer circle. And the inner circle is called, in the definition of a predicative polymorphic lambda calculus, this inner circle is called monotype. And the outer circle is called polytype. This looks ugly. So let me draw everything again. So the key idea, the key point in the design of predicative polymorphic lambda calculus is we stratified the set of types into two layers. The first inner layer, which consists of this function type, and the outer layer which includes this polymorphic type. And for simplicity, we call the inner circle as monotypes. Monotypes are shortened for monomorphic types. Monomorphic types. And the entire set of types is called a polytype, a shortened for polymorphic types. And we'd like to syntactically distinguish between this one and this one. So that's pretty much the essence, the key idea in the design of predicative polymorphic lambda calculus. Then what about type variable alpha? The question is, where does this type variable belong? Should we write the type variable alpha here or here? And it turns out that this type variable itself is not polymorphic. Type variable, say we have type variable alpha, later it will be something like int or bool and so on. So type variable itself is not polymorphic. Simply speaking, a polytype must have this type quantifier, something like for all alpha, for all beta, and so on. And simply speaking, this type variable alpha does not start with this type quantifier. So therefore, alpha actually belongs to monotypes. So for instance, we can have alpha arrow alpha. This is definitely monotype. It's not polymorphic type because we don't have this type quantifier. So to answer the question, this type variable alpha belongs to the inner circle, the set of monotypes. So we should remove this alpha here. So now we stratify the set of types into two layers, the inner layer called the monotypes and the outer layer called polytype. Now let's turn this diagram into the formal definition of syntactic categories, two syntactic categories. So here's the definition, monotype and polytype. So let's use method variable a for monotype. So it has this function type and type variable. And polytypes, we use this method variable u. It must start with, for all alpha, this type quantifier, and then it's followed by u. And if it does not start with this type quantifier, it must be a monotype. So just as indicated by the presence of inner circle inside this outer circle, these polytypes of course include the set of monotypes. So in other words, a monotype is a particular class of polytypes which happen to start with no type quantifier. So polytypes of course includes everything from monotypes. So now we have two syntactic categories for types. So we have now two layers, monotype layer and polytype layer. And according to the definition here, a polytype U is always of this form. In general, you have for all alpha, for all beta, for all gamma, and so on. And in the end, you must have this monotype. So perhaps you have something like A arrow A. And of course, you could have something like U is for alpha, alpha, but perhaps this is not very useful. So this is a typical pattern of constructing a polytype. And in the other literature, this polytype is also called types written in prenex form. So we don't really need this terminology, but prenex form, because this series of type quantifiers always appear in the prefix. So here this denotes a prefix. So we say that a type written in this form is written in the prenex form. So now we have finished introducing the two different sets of types, monotype and polytype. And what about expressions? Expression E is variable, lambda abstraction. But here's an important part. Of course, we have this lambda application. If we look at this function type in the definition of a monotype, this is a function type. So therefore, the argument must have monotype. This argument must have this monotype. It's not polytype. That is, we don't allow something like this. This is not allowed. If we allowed this form of lambda abstraction, then the whole definition degenerates into system F, or the whole system evolves to system F and introducing undecidability again. So this must be disallowed. That's the whole point in introducing predicative polymorphic lambda calculus. So remember that here the types are restricted to monotypes, not polytypes. You can never have polytypes here. And then we have type abstraction and type application. And here's another important part. We could have either E applied to type A or E applied to polytype U. And as you might have guessed already, this is what we take. This is what we disallow. Because the whole point in developing predicative polymorphic lambda calculus is this type variable is restricted to range over only to the inner circle. We don't want to instantiate this type variable to another polymorphic type because then we witness something called referential phenomenon, referential stuff. Then the instantiation becomes self-referential, it becomes self-referential. So in order to forestall this self-referential phenomenon, we allow only monotype in type application. So this is never allowed. And that's also another critical part in the definition of predicative polymorphic lambda calculus. So that's the definition of expressions. What about values? Values, we have lambda abstraction and type abstraction. And for typing context, the definition is the same. So it's either empty or this type binding and this type variable declaration. But unlike in system F, where we happen to use the same meta variable for monotypes in predicative polymorphic lambda calculus and A for types in system F. So it may appear like there's no significant difference between the two languages, but there is a big, really significant difference. The first is here, this lambda abstraction can take only monotype. You cannot pass polymorphic functions. And secondly here, you can never instantiate type variable to polymorphic types. You can instantiate the type variable alpha only to a concrete monotype. So here, this is a monotype. Not every type permitted in the language. It is monotype. So this is the syntax for predicative polymorphic lambda calculus. Now, Now let's develop the type system first. So what about type system? So we do two kinds of judgment, type judgment and typing judgment. Typing judgment says under typing context gamma, expression E has a type U. Notice that here we allow polytype because we can definitely create expressions of polymorphic types. So for example, later we will see how to implement polymorphic identity function, which is actually the same as in system F. So in other words, the presence of U here, not A, implies that this can be polymorphic type. So this expression can have a polymorphic type. So this language is polymorphic type. This language allows polymorphic expressions. But in contrast, the type judgment only allows monotype because as we will see, the construction of polytypes is automatically valid. Any polytype constructed according to this syntax is legitimate, provided that all the monotypes are legitimate. So we are going to use these two judgment, type judgment, this one, and typing judgment, this one. And because we have seen the type system for system F, the development of type system for this language is actually quite straightforward. So let's first review this one. So remember that the set of monotypes are comprised of these function types and type variable, and that's all. So first, how do we check the validity of this function type? Well, we have to verify that A is okay, and we have to verify that B is okay. What about this type variable? This type variable is okay to use only if this type variable has been declared in typing context gamma already. So these are the type rules. Now let's talk about these typing judgments, the typing rules. First, what is the type of this variable x? It must have a monomorphic type because, let's go back to the important restriction here. This lambda abstraction allows only monotype, so variables can have only monotype. So this variable x can have only monotype if this type binding is found in the typing context. And what about this lambda abstraction? Well, it's just like the system F stuff or simply type lambda calculus. So we augmented the typing context with this new type binding and check if expression E has type B. Type application, it's also the same as before. If expression E has a type A, arrow B, and expression E prime has a type A, then expression E applied to E prime has a type B. Now what about these polymorphic types? Now we have this type abstraction. And just like in system F, we introduce this fresh type variable, alpha type, and then we find that the type of this expression U, which can have a polytype in general, not monotype. And then this type abstraction has a type for alpha U. What about type application? So remember that in the definition of expressions, this type application allows only monotype. You can never use polytype in place of A here. So this is not permitted. So we have this A here. So needless to say, expression it must have some polytype. And then we have to make sure that A is valid, it's well formed. So notice that we don't need a more general form of type judgment. So this is enough. And then the whole expression has type A for alpha. So we see type substitution in type U. So this is called for all introduction rule, and this is called for all elimination rule. So that's the type system for predicative polymorphic lambda calculus. Now, why is it that this language is fine? So we go back to here. So here we have predicative polymorphic lambda calculus. So it is positioned at the left extreme end, whereas system F is positioned at the right extreme. So system F is too powerful, but it has this downside of being undecidable. Type reconstruction is undecidable. And in the case of predicative polymorphic lambda calculus, precisely the opposite happens. The type reconstruction is of course decidable. So we will not see why this is decidable, because later we will see more powerful language that is still decidable. So as a corollary, predicative polymorphic lambda calculus is automatically decidable. I mean, the type system is automatically, type reconstruction is automatically decidable. But the funny thing is, this predicative polymorphic lambda calculus allows polymorphic expressions. We can definitely write, for example, polymorphic identity function, capital alpha, lambda x, alpha x. But it's completely useless. That is, it is the least powerful language we can think about with polymorphic types. It is a type reconstruction decidable, but it's completely useless. So let's see why this language is useless. So the main problem with predicative polymorphic lambda calculus is polymorphic expressions cannot be used polymorphically. So in other words, polymorphic expressions, you can definitely write the polymorphic expressions in this language, but these polymorphic expressions can be used only monomorphically. Only monomorphically. So here's an example. Suppose that we have this polymorphic identity function. So it has type for all alpha, alpha arrow alpha. So the expression would be this type abstraction, lambda abstraction with body x. So it has type for all alpha. We introduce variable of type alpha, and the body is of the same type. So the body has type alpha, arrow alpha. So therefore, this expression has type, is polymorphic type. So we can write the polymorphic expressions, but the motivation for writing polymorphic expressions is to be able to apply this expression in different contexts. For instance, we'd like to be able to apply the same identity function to Boolean true, for example. And also, we'd like to be able to apply the same polymorphic identity function to integer 3 in a different context. So we have totally different context here. and we'd like to reuse these polymorphic expressions in different contexts. So in this case, we would have to instantiate the type variable alpha to, for example, bool. And here, we have to instantiate the type variable alpha to int. So if this was feasible, then everything would be fine. But the problem is, this is infeasible. This is impossible to write in this language. And let's see why. So in order to apply the same identity function in different contexts, we have to first bind this expression in some variable. So the idea is this one. We have this polymorphic identity function. And in order to reuse this polymorphic identity function in different contexts, we'd like to bind it to in a variable. Let's just say this is f. F must have some type. And then inside of the body of this lambda abstraction, we'd like to apply f in different contexts. So for instance, f to true and f to integer 3 or something like this. So this is confusing. So let's write the equivalent expression in untyped lambda calculus. In untyped lambda calculus, we would write the example this way. Give me a function f, and let me apply the function f to boolean true, and the same function f to integer 3, and then pair the results up. So let's assume that we have implemented this pair construct, and then we apply this function to this identity function. Now, we define this identity function only once. Here we define the identity function, and we reuse it in different contexts. Here with the Boolean argument, and here with an integer argument. So we achieve this polymorphic application of the same expression. We have this function, identity function, applied in different contexts. So if we could rewrite this expression in predicative polymorphic lambda calculus, then everything would be fine. But unfortunately, this is impossible to rewrite in this language, in the predicative polymorphic lambda calculus. So let's see why. So I'm going to try to, so let me try to rewrite this example in the syntax of predicative polymorphic lambda calculus. So you have lambda f of some type, and then we are going to apply f to true and f to 3, and then we apply the whole function to this polymorphic identity function for alpha lambda x alpha dot x. But we see immediately that there's something wrong in this attempt, because the argument has this polymorphic type, whereas this formal argument, this variable f, is expecting a monotype. So if we go back to the definition of type, function type, the function type only allows monotype here. This is A, not U. So in the definition of a function type, the argument must be of monotype, and the return type must be also monotype. So in other words, functions, lambda abstractions here cannot take a polymorphic argument. So therefore, we cannot write something like for all alpha arrow A here. It's syntactically ill-formed. Then we can never pass this one over here. And this is the reason why we cannot actually we cannot rewrite this example in this polymorphic lambda calculus, predicative polymorphic lambda calculus. We might attempt in a different way. So for instance, because this one allows only monotype, perhaps before applying the function, you could instantiate it to Boolean type. So for instance, capital lambda alpha, lambda x, alpha x. So we apply this one to Boolean type. Then the argument now has monotype bool arrow bool. And then f could be assigned type bool arrow bool. Then we can apply this f to true, Boolean constant to true. But the problem is now the opposite. We were able to pass this function to this lambda abstraction. Now you can apply this function f only to Boolean constants, not integers. So in other words, you are not able to apply the function polymorphically. So this example shows that the restriction on the syntax at the level of a syntax just defeats the whole purpose of introducing polymorphic types. You can define these polymorphic expressions only to apply them monomorphically, never polymorphically. So that's the reason why this is essentially useless. This language is useless. So to make sure that everyone understands why this doesn't make sense, you cannot, first of all, pass this polymorphic identity function to this lambda abstraction because this f must have monotype. But this has a polytype. So type checking fails for this expression. So you cannot even make attempts to apply the function f to different types. This doesn't make sense because you cannot pass this expression to this lambda abstraction. And if you instantiate it in advance, for example, to Boolean type, then we lose the utility of this polymorphic identity function. There was no reason whatsoever to introduce this polymorphic identity function because we only use it monomorphically. So perhaps the more practical approach would be, instead of taking this detour, we could directly write this lambda x bool x without having to create this polymorphic expression and then instantiating with this Boolean type. So this is just nonsense. We might just as well create this lambda abstraction directly. Then you can never use it polymorphically. So the bottom line is, in the case of predicative polymorphic lambda calculus, the problem is, yes, we can define polymorphic expressions of polymorphic types, that is, expressions with polymorphic types. So superficially, the language is polymorphic. The type system is polymorphic. However, in practice, it is useless. In practice, it is useless because you can never pass polymorphic expressions to lambda abstractions. So you can never use these polymorphic expressions with the polymorphic types polymorphically, really polymorphically. You can define, for example, polymorphic identity function of type for all alpha, alpha, arrow, alpha, only to use it monomorphically. So for example, only for type bool. In which case, why do we bother with this polymorphic identity function? we might just as well create identity function specialized for bool directly, bool arrow bool. So this is the problem with predicative polymorphic lambda calculus. So finally, I'd like to compare the two languages, predicative polymorphic lambda calculus and system F one more time. So this is the set of types that system F allows. So you can have this function type and type variable and polymorphic type. And there's no separation between monotypes and polytypes. And this is the set of types in predicative polymorphic lambda calculus. And here we stratify the set of types into two layers. So we have this inner layer, monotype, and outer layer called a polytype. So here we have A arrow A and type variable, and here we have this polymorphic type, pol alpha U. And if we compare the set of types here and the set of types here, it turns out that this goes to inside here. So in other words, there are some types that can be written in system F, but not in this predicative polymorphic lambda calculus. Because even though here we can write the polymorphic types, these polymorphic types must be written in Prenex form. It must have this form for all alpha, for all beta, for all gamma, blah, blah, blah. And then maybe some function type, A arrow B. This is the only form of polymorphic types that we can have in this language. But in system F, there's no restriction. So for example, one example would be here, a function that takes polymorphic type and return another polymorphic type. So this is not expressible in this language. So the set of types allowed in system F is strictly larger than the set of types allowed in predicative polymorphic lambda calculus. As a side note, an alternative name for system F is impredicative polymorphic lambda calculus. And the reason that we have two different names for essentially the same language is this language was discovered independently by two different people almost simultaneously. So that's the reason that we have two names for the language, for the same language. And impredicative polymorphic lambda calculus stands in contrast to this language because it's really predicative. So there's no form. It's hard to formally explain the meaning of impredicative, but you can think of it as self-referential. So we learned the phenomenon self-referential stuff when we are motivating the development of this language. So you can equate this impredicative to self-referential. In system F, type applications can be self-referential. A type variable can range over polymorphic types, but that's not permitted in this language. So this language is called, instead of impredicative, it's called predicative polymorphic lambda calculus.